An engineer logs into a server with a standard request. Provision a single 10 gigabyte storage volume for a new database. They execute the standard Linux ls block command to verify the newly attached storage. But instead of one new drive, the terminal displays 4 separate 10 gigabyte block devices: SDB, SDC, SDD, and SDE. The request was for exactly one disk. The system is presenting 4. A junior administrator might assume this is a provisioning error, that the storage team accidentally cloned the volume 4 times. But this is not a mistake. Those 4 identical entries are the exact digital footprint of a perfectly configured, highly resilient enterprise architecture. To understand why, we have to look behind the server and into the invisible infrastructure powering it, the Storage Area Network, or SAN. Unlike the direct attached storage inside a laptop or a standalone server, where a drive connects straight to a motherboard, a SAN entirely separates the storage hardware from the computing host. To see why Linux registers 4 disks instead of 1, we have to reverse engineer the physical journey of that data, tracing it from the host operating system all the way down to the bare metal. The confusion at the terminal happens because we are viewing enterprise-grade redundancy through the simplistic lens of a consumer PC. At the absolute lowest layer of the data center sits the Disk Array Enclosure, or DAE. This is the physical chassis packed with raw hard drives. At enterprise scale, hardware failure is a statistical certainty. Individual physical disks will constantly degrade and die. To absorb these failures, hardware RAID intercepts the raw storage and binds it together mathematically. The system clusters multiple physical drives into a single logical unit called a virtual disk. This virtual disk is an abstraction layer, hiding the physical boundaries of individual drives. Within that array sit hot spares, idle drives waiting in silence. If an active drive fails, a spare instantly replaces it, rebuilding data while the virtual disk remains intact. We cannot expose a massive virtual disk to every server. That creates chaos. Instead, administrators carve out an isolated slice, the logical unit number, or LUN. Sitting atop this array are the brains of the operation, storage processors SPA and SPB. These twin processors act as dual redundant gateways. If one processor fails, the other continues routing data, ensuring the controller itself never becomes a single point of failure. So the hardware RAID and the dual processors create an invulnerable physical array. But at this stage, that 10 gigabyte LUN is still completely isolated from the database server that needs it. To move data from the isolated array to the server, we use a dedicated storage area network built on fiber channel cables. While traditional Ethernet relies on electrical currents moving through copper wire, fiber channel encodes data into pulses of light shooting through glass optics, allowing for massive, high-speed throughput. At the center of this network sit dual fiber channel switches, Switch A and Switch B. Looking at the topology map, we see a crisscross cabling method. Storage processor A connects to both Switch A and Switch B. Storage processor B duplicates this, also connecting to both switches. This dense web of connections is an open fabric, meaning every device plugged in could theoretically see every other device. Without strict authorization, servers would overwrite each other's data. To prevent this, administrators use 2 security protocols. The first is LUN masking, executed directly at the storage processor, which explicitly assigns a LUN to a specific server. The second is zoning, which happens at the fiber channel switch. Zoning acts as an access control list, ensuring only authorized devices can even communicate across the fabric. Zoning enforces these rules by locking connections using unique, permanent hardware identifiers called worldwide port names. By combining physically crossed cables with rigid access controls, the network fabric protects the LUN in transit, ensuring it safely reaches only its intended target. That target is the Linux server requesting the database storage. It sits at the top of our topology map. The server uses hardware cards called host bus adapters, or HBAs. HBA1 extends a connection down to Switch A, and HBA2 connects down to Switch B. Looking at the complete map, data can travel along 4 distinct routes to reach the single LUN. Even with the hardware physically wired and zoned, the Linux operating system kernel remains completely blind to the new storage. To discover the LUN without rebooting a live production machine, the system administrator must manually force an online SCSI bus scan. They do this by echoing 3 hyphens, representing the controlling, the target, and the LUN ID, directly into the server's sysfs directory. This command forces the Linux kernel to send queries down through the HBA ports and across the Fibre Channel fabric, mapping whatever hardware responds. The query travels down all available connections. As a result, the kernel discovers the exact same 10 GB LUN via all 4 physical paths. Because the kernel evaluates hardware based on the pathway the response took, it treats each of these 4 routes as a discrete piece of storage. This solves the paradox. The operating system isn't hallucinating, and no one cloned the drive. Linux is simply translating 4 physical lifelines into 4 raw block devices: SDB, SDC, SDD, and SDE. But stopping here is a trap. If an administrator formats a file system directly onto SDB, they commit a catastrophic architectural error. Writing exclusively to SDB hard-codes the operating system to rely on only one specific physical pathway through the network. If a single switch or cable on that exact route fails, the server loses access to the disk. The database crashes instantly, rendering the multi-million-dollar physical SAN redundancy completely useless. To fix this, we rely on dynamic multipathing daemons, either native to Linux or running as third-party tools like PowerPath. The multipathing software interrogates the SCSCI inquiry data returning from the array, reading the worldwide identifier of the storage volume. It recognizes that all 4 block devices share the exact same identity. The software then intercepts these 4 raw paths and collapses them into a single unified virtual block device, commonly labeled MPath-A. With the paths combined, the software actively load balances traffic, distributing requests across all 4 connections to maximize bandwidth. Crucially, it provides seamless failover. If a switch or cable fails, data instantly reroutes through surviving connections without interrupting the server. Now, the administrator can safely initialize this single consolidated MPath device as a physical volume. This physical volume is then fed into the standard Linux Logical Volume Manager pipeline, where it is formatted, mounted, and finally handed over to the database. True high availability is a 2-part harmony, an invulnerable hardware fabric running below the server, matched perfectly by intelligent, abstraction-aware software operating within the OS.